All right, so this video is going to be on just a few things, interesting alkenes, lipids, and fats, as well as a little bit of other information, but it's more of an informative one, kind of fun actually, because we'll talk about leaves and whatnot. I know y'all like biology. So the ethylene is the most simple alkene, right? And so that's a building block for polymers. And so this guy right here is a polymer. It's a polyethylene, the one with the chlorine. Sorry, let me just write polyethylene first. The one with the chlorine is PVC, polyvinyl chloride. Okay, and so that actually is because we have a chlorine on a vinyl. It's a vinylic chlorine, right? It's on the vinyl position, and so that's where PVC comes from. And this particular polymer is an acetate. Okay, so we have an ester there, right? And so this is polyvinyl acetate. And you might guess what the structure is based off of the name, but yeah, it's a vinylic acetate group. Okay, so we've got another polymer here with the phenols there. Remember, phenyl pH is the benzene ring. Okay, and so this is polystyrene's structure, and it looks like this. That's what styrene looks like, and that's how you make polystyrene, which is styrofoam, right? So, and I didn't mention it, but the squiggly lines are basically cutting off the molecule because the polymers are very large molecules, and they're linked hundreds or thousands of those monomers all together. But the question is, why do leaves change color in the fall? Not just because we enjoy it. They actually don't change much around here, but as much as other places. But we got some nice colors going on. I see a lot of beautiful trees. So here, first I want to talk about, I'm going to do a very poor attempt at drawing chlorophyll. So here's just a portion of it, right? So definitely sick of drawing those 5-membered rings. I'll go ahead and draw circles to indicate those, but the circles represent 5-membered rings like above. And there's some other stuff on here for sure. I'm simplifying the heck out of this. But the cyclic thing, so kind of sequestering that magnesium, is called a porphyrin. Okay, and so when you do it with as well as some of those R groups on there, that's chlorophyll. The cool thing about porphyrins is that's pretty much what makes up our hemoglobin as well. So but let's talk about the yellow colors of leaves. Okay, so lutein, which is a carotenoid, looks like this. All right, bear with me because it's about to be is a long road to lutein. Okay, so tons of double bonds, which are alkenes, right? That's why we're talking about this. These are some interesting alkenes to me because I love the different colors of leaves that we get to experience in autumn. Or fall, and this is the structure of lutein, and that's what gives the leaves their yellow color. Okay, so I didn't mention it, but when there's not a significant amount of sun and there's like colder temperatures, that's when chlorophyll production kind of slows down, and so lutein is always present. Chlorophyll is more abundant in the summer months or spring maybe, and then the warmer sunnier climates or warmer sunnier times of year. And so when that production of chlorophyll, which gives it that green color, kind of slows down, we still have degradation of these larger alkene molecules like beta carotene drawn here, which gives it the orange color. But since they decompose much slower than chlorophyll, their population of them or concentration of them is much greater, and so that's why essentially those colors end up winning, right? And it's all about absorption of light, right? So if you're seeing a given color, such as let's say orange, right, that means you're reflecting red and yellow, because red and yellow make orange, and we are not absorbing the red and yellow, we're absorbing like the green or the blue. And yeah, so that's pretty much it. We don't need to get into the absorption and UV lights or like orbitals and anything of that sort, but I just wanted to show you all of these really important alkenes that we experience or we see every day, but you might not really realize it, right? I really like this violazanthin too above because it has an epoxide in there. Say what? Serious right now? Are you serious, Jess? Come on. This is wild. We're like in autumn and we're talking about epoxides and alkenes and we have violazanthin, which has both of them. Yeah, chemistry is everywhere, y'all. Don't get it twisted. It's super important and everywhere. Especially lycopene because we got some dancing tomatoes. That's what gives you that red color. We always talk about lycopene being important, right? It's in ketchup because it's in tomatoes, gives you the red color. Well, it's in leaves too. And also those anthocyanins, which you might be familiar with from general chemistry because anthocyanins are the reason why red cabbage can be used as an indicator, a pH indicator. Super fun experiment. You can actually use like other things too, like blueberries are pretty much things that have anthocyanins in it, which is apparently the things that are red, right? Or have that color and mixed in. So another one that I also want to mention is the stuff that's in ginger, because ginger is hashtag my fave. And I always mess up this name. Zingerberine is zingerberine. I like ginger. I'm gonna go with ginger. I feel like they're messing with me calling it zingerberine, whatever it is. But that's the structure of it. Has alkenes up the wazoo, right? So that's pretty much it for the interesting alkenes. Not that all the other ones aren't interesting, but that's kind of like the ones that I want to talk about, right? So lipids have alkenes in them as well, which we already know, whether we know it or not, or whether we are aware of it or not. But okay, so this compound right here is a triacylglycerol, and those R groups can range from 11 to 19 carbons in length. Okay, so they're really long carbon chains, essentially, right? Which is non-polar, right? And that's why they are the lipids, the fats, the oils, right? So this is an ester functional group, as you know, and so it reacts like an ester. And again, those triacylglycerols, I'm going to abbreviate as TAGs, which you probably have seen before. Okay, so I mentioned that they react like esters, right? Because they are esters. Well, esters can hydrolyze, so undergo hydrolysis or splitting of water. So we use water and acid or base or an enzyme, and we can split it up into an alcohol as well as a carboxylic acid or a carboxylate. It depends on if it's a carboxylate, then that means we used hydroxide. So we form a fatty acid if it's a acid catalyzed hydrolysis of a triacylglycerol, but otherwise it's going to be the carboxylate. Okay, that's actually what they do in the movie Fight Club. They use lye, which is concentrated sodium hydroxide, and they go to a liposuction place to get fat and make soap out of it. All right, so trying to fill in the blanks while I draw these large molecules. We're about to draw a bunch of these large molecules, but fatty acids are basically the byproduct of hydrolysis of a triacylglycerol, right? Stearic acid is, all of these ones will have 18 carbons, okay? And so stearic acid, as you can see, is just a bunch of CHs. Oleic acid does have a cis alkene in it. Linoleic acid also has cis alkenes, but it's more than one. We're going to have these two here, as well as the terminal carboxylic acid. And then the last one is not linoleic, but linolenic. Okay, linolenic. We've that kind of reminds me of Tommy Boy, I think. Black Sheep, maybe. I don't know. Roads. Anyway, we've got an alkene here. Boom. Okay, so as you see, you can see that it goes from, we have none on the top, and then we get 1, 2, and then 3, right? So this is important to point out because we can see the trend in the melting point go down. So stearic acid having none is 69 degrees, oleic is 4, linoleic is -5, and linolenic is -11. So as you can see, the more double bonds we have in it, holy moly, The more double bonds we have in it, the lower the melting point. And what does that really mean in practical applications? That means that we have more double bonds in the liquid fats, right? So like olive oil, for example, is a liquid at room temperature. And that's because it has more double bonds. Whereas fats from animals, maybe like butter, or if you make like a stew or something, you have that the fat solid on the top of it. That is solid at room temperature as well, because it doesn't have any double bonds, or it has very little. Okay, so those kinks in there, they prevent easy stacking, and so therefore you're limiting the amount of intermolecular forces that can occur, and so that's why you're lowering the melting point. Okay, naturally occurring fatty acids are cis or Z configuration, and so that's an important factor, because we always talk about trans fats or omega fats, right? So let me tell you what that means. The top fat is completely saturated because it has all of its hydrogens they can have, right? That's the definition. And that's why we call things saturated fats, right? Well, these other two on the bottom, or any of them, oleic acid, linoleic acid, and linolenic acid, they all have alkenes. And so these are unsaturated fats. And specifically, linoleic is an omega-6 fatty acid because it has the first double bond occurring 6 carbons from the ends. And then linolenic is omega-3 because it has the first double bond occurring 3 carbons from the end. And that's where omega-3 and omega-6 fatty acids comes from. Now you know. Cool stuff, right? So the last thing I want to mention about these guys, which is kind of fun facts, right? Is we have cis fats naturally occurring. We already mentioned that. And then trans fats, we always hear like, oh my gosh, those are so terrible for you. Don't do that because you're going to explode or something. Well, trans fats is literally when you have that alkene, but it has trans orientation. Okay, so it's all about stereochemistry. I told you, man, it's everywhere. So if you're ever curious, you can ask me like, how does that happen? It's not naturally occurring though, as we said. That's cis fats. Okay, so fats versus oils. This is pretty straightforward. Fats are solids, and they're solid triacylglycerols. So they're made from the fatty acids that have few or no pi bonds. So like the stearic acid. And then the oils are the ones that are liquid triacylglycerols, and those are made from the fatty acids that have lots of pi bonds. Okay, so that was like the oleic or linoleic or linolenic acid. Okay, and then the fats are typically going to be from animals. So we see, again, you make a stew, you let that stew cool, the fat goes to the top and it solidifies, and then it's gross, but it's super yummy. And I mean the stew is yummy. You scoop the fat solid off the top sometimes. But anyways, that's it for the interesting stuff. All right, let's move on to how we make alkenes in another video.